It is very hard for archaeologists to explain how that was done using purely leverage and mechanical advantage.
Something happened in the granite quarries of Aswan, in southern Egypt, and even now the stone does not seem finished telling the story. The evidence is still there, cut directly into the bedrock. Long, smooth scoops. Repeating arcs. Curved channels carved into one of the hardest natural materials on Earth. They sit under the desert sun exactly where they were made thousands of years ago, silent, visible, and strangely resistant to easy explanation. For more than a century, those marks have been described in broadly familiar terms. Ancient Egyptian workers, armed with stone pounders, copper tools, patience, discipline, and astonishing endurance, shaped the granite by hand. That explanation is not absurd. It is not invented out of nothing. Archaeologists do have evidence that dolerite pounders were used in Egyptian quarries, and anyone serious about this subject has to begin there. But the problem begins when you look closely. Because some of the marks at Aswan do not look like rough impact damage. They do not look random. They do not look like the cumulative effect of endless irregular blows delivered by workers crouched in cramped trenches, swinging heavy stones at awkward angles. Many of them look smoother than that. More controlled. More repeatable. More consistent than the conventional story comfortably predicts. And in recent years, that tension has been sharpened by a new kind of attention. Not human intuition alone, not casual visual comparison, but computational analysis applied to the geometry of the marks themselves. AI-assisted image study has entered a debate that was already old when the modern discipline of archaeology was young. And while artificial intelligence has not solved the mystery, it has done something important. It has forced the question into sharper focus. Not, does this look unusual? But, exactly how unusual is it? Not, could ancient workers have done this somehow? But, what specific tool motions, material interactions, and cutting methods best match what is physically preserved in the granite? That difference matters. Because once the question becomes precise, the quarry becomes harder to ignore. To understand why Aswan matters, you first have to understand granite itself. Granite is not a forgiving material. It is not soft limestone that can be shaped relatively easily with copper chisels and abrasion. Granite forms deep underground under heat and pressure over immense spans of time. It is dense, crystalline, hard, and resistant. On the Mohs scale, it generally falls around 6 to 7, depending on composition. Copper, by contrast, is far softer. That basic mismatch has troubled researchers for generations. Of course, the issue is more nuanced than a simple hardness comparison. A softer tool can still help cut a harder stone if it carries an abrasive that is itself hard enough to do the actual work. Quartz sand, emery-like abrasives, corundum, and other particles complicate the picture. The ancient tool is not necessarily slicing the granite directly. It may be acting as a holder, a guide, a pressure surface, or a carrier for the real cutting agent. That is why the old question is not merely, could copper cut granite? The better question is, what full system of tool, abrasive, lubricant, motion, and control did ancient Egyptian workers actually use? And that is where Aswan becomes so important. Because Aswan is not just any quarry. It supplied some of the most important granite in ancient Egypt. Red granite for obelisks, statues, temple elements, sarcophagi, and architectural components that still define Egyptian stonework in the popular imagination. It is also home to one of the most revealing unfinished objects in the ancient world, the unfinished obelisk. The unfinished obelisk matters because it preserves process, not just result. Finished monuments can awe us, but they hide their own making. They have been polished, transported, erected, integrated into architecture, and stripped from the practical context of production. The unfinished obelisk is different. It was abandoned in place after cracking during extraction. It never left the quarry. It was never completed. It remained where the workers had been cutting it free from the bedrock, and because of that, it gives us a rare chance to inspect the scars of the work itself. Along the sides of the extraction trench and across quarry surfaces nearby are the marks that have fueled this debate for decades. Curved scoops. Repeating hollows, broad, arcing depressions that seem, to many observers, smoother and more uniform than dolerite pounding alone would naturally create. This is where older scholarship becomes relevant. In the late 19th century, Sir William Flinders Petrie studied Egyptian stoneworking evidence closely, including drilling marks in granite. He concluded that some ancient drilling appeared to involve cutting rates and precision difficult to explain by the simplest conventional models. Petrie even entertained the use of very hard abrasives, possibly including corundum, which is far harder than granite. His observations were never meaningless. But over time, the larger public narrative about Egyptian stoneworking often settled into a simpler explanation: copper tools, stone pounders, sand abrasives, and immense labor. That explanation contains truth. The problem is that truth may be incomplete. Dolerite pounders unquestionably belong in this conversation. Archaeologists have found them. There is real evidence that they were used. When granite is pounded by hard stone, it can indeed be fractured, bruised, and gradually reduced. Experimental archaeology has shown that. But experiments have also exposed the limits of the method. Pounding tends to create rougher textures, fractured edges, and more irregular impact signatures than some of the smoother arcing marks visible at Aswan. That does not automatically mean the orthodox view is wrong. It means the orthodox view may not be sufficient on its own. And this is where AI-assisted analysis has captured so much attention. When researchers and enthusiasts fed high-resolution images of quarry marks into modern image analysis systems, the goal was not to summon a magical answer from a machine. At least, in the best version of the exercise, the goal was more modest: measure what can be measured. Compare widths, depths, spacing, curvature, orientation, recurrence, and consistency across large numbers of visible marks. Ask whether the resulting pattern looks more like random impact, guided abrasion, rotational cutting, constrained hand motion, or something else entirely. The intriguing claim that emerged from these analyses was not simply that the marks are neat. It was that many of them may be quantitatively more regular than casual inspection suggests. Some analyses have claimed low variation in mark size, repeated arc geometry, and consistent spacing across quarry surfaces. If those findings hold up under rigorous independent study, then they matter, not because they prove lost technology, but because they define the problem more precisely. Human labor leaves variation. Skilled labor reduces it, but rarely erases it. When someone works stone by hand, especially in cramped or exhausting conditions, small differences accumulate. Angle shifts. Force changes. Fatigue intrudes. Reach becomes awkward. Visibility worsens. Access alters the motion. Over time, these differences typically show up in texture. Yet one of the most interesting arguments made by AI-based reviewers is that some Aswan marks appear consistent even where human body mechanics should have made consistency harder to maintain. Marks appear in tight corners. Marks continue along constrained surfaces. Marks show similar curvature in areas with very different accessibility. If true, that pattern raises an uncomfortable question. How did workers maintain such regularity where a person with a handheld pounder should have been at a physical disadvantage? That is not proof of machines. It is proof of a better question. Maybe the answer lies in guided tools. A handheld tool does not have to be free-floating. Ancient workers may have used templates, fixed pivots, braced shafts, sledged abrasives, or constrained motion setups that have left little or no direct archaeological trace. Even simple mechanical guidance can dramatically increase repeatability. A pivoting arm can create a regular arc. A braced shaft can stabilize angle. A groove following abrasive motion can produce repetitive curvature that resembles machine work without requiring electricity, motors, or steel factories. That possibility deserves far more attention than it usually gets, because it offers a middle ground between two bad habits: the habit of underestimating ancient craftsmen and the habit of leaping straight from unexplained precision to technologically impossible fantasies. Still, the mystery deepens in certain parts of the quarry. Among the most puzzling features at Aswan are narrow, deep pits and extraction trenches that seem, at least visually, difficult to reconcile with unrestricted manual pounding. Imagine a worker deep inside a narrow shaft or wedged along a trench wall, repeatedly swinging a heavy stone in a controlled arc. Even if possible, it seems operationally awkward. Dust accumulates. Chips have to be cleared. Lighting becomes poor. Body position deteriorates. Yet some walls appear to preserve surprisingly consistent surface treatment. Again, we should be careful. The eye can overread patterns. Surface weathering can blur some marks and exaggerate others. Photographs can deceive. But the persistence of the question is itself significant. The same objections return because the same visual problem returns. Some modern commentators push this much further. They claim microscopic analysis reveals spiral signatures of rotary cutting, traces of high-speed heat effects, or evidence of advanced abrasives comparable to modern industrial methods. These claims are dramatic and should be treated cautiously unless backed by transparent methods, sample chains, and peer-reviewed publication. Yet even without leaning on the most sensational versions, the larger challenge remains. Conventional explanations often describe broad capability, but not always the observed precision. That distinction is important. It is one thing to show that granite can be worked with stone pounders and abrasives. It is another thing to show that the specific marks at Aswan, in their geometry, smoothness, and spatial distribution, are best explained that way. Those are not the same claim. The debate is often muddled because people switch between them. They say, experimental archaeology proved Egyptians could shape granite, as if that automatically settles every quarry mark and every extraction surface. It does not. Demonstrating possibility in general is not identical to matching the details of a specific case. And so the Aswan question stays alive. What exactly do the marks record? Impact, abrasion, rotational cutting, guided scraping, oscillation, multiple stages of work, preliminary roughing with dolerite followed by smoothing with abrasives, a workflow involving more than one tool class. The more seriously you ask these questions, the less satisfying simplistic answers become. At this point, it is worth pausing to say something important. Mystery is not the same thing as magic. Ancient Egypt does not need aliens, forgotten supermachines, or science fiction interventions to be impressive. The civilization already produced achievements of staggering scale, organization, geometry, logistics, and endurance. Underestimating ancient people is just as irrational as romanticizing them into impossibility. The real intellectual task is harder and more interesting than either extreme. It is to reconstruct technique from stone. And stone is a stubborn witness. It preserves outputs far better than it preserves process. Wood decays. Rope disappears. Organic components rot. Lubricants vanish. Metal corrodes or is recycled. Workshop setups are dismantled. Temporary rigs leave little trace. What survives best is the worked granite itself and, occasionally, the stone tools nearby. That means absence of surviving machinery is not definitive proof that no guiding devices, composite tools, or specialized rigs ever existed. At the same time, absence of evidence is not license to invent anything we want. It simply means humility is required on both sides. One reason the Aswan discussion continues to attract so much public attention is that it sits at a crossroads between visible fact and interpretive uncertainty. Anyone can see the quarry marks. Anyone can understand that granite is hard. Anyone can appreciate how difficult it would be to cut monumental forms out of bedrock. The mystery is not locked away in equations. It is out in the open. And because it is visible, people feel the tension immediately. That visibility has made Aswan a magnet for alternative history narratives. Some claim the quarry proves ancient high technology equivalent to modern machinery. Others go further and argue that the finest work predates dynastic Egypt entirely, belonging to a lost civilization later inherited by the pharaohs. These ideas are compelling because they offer clean dramatic solutions to a messy problem. But clean dramatic solutions are often the least reliable ones. A more disciplined reading of the evidence points somewhere subtler. It suggests that ancient Egyptian granite working, especially at its highest levels, may have involved a toolkit and procedural sophistication that we still have not fully reconstructed. That sophistication may have included hard abrasives, careful lubrication, guided motion, staged cutting, systematic quality assessment, and quarry planning more refined than popular summaries admit. In other words, the mystery may not be that ancient people had impossible technology. The mystery may be that we have been telling too simple a story about how they worked. That possibility becomes even more interesting when we zoom out beyond Aswan. Egyptian stoneworking more broadly contains multiple examples of remarkable precision. Drilled holes in hard stone, smooth internal surfaces, tight joins in monumental masonry, polished granite chambers, enormous monolithic elements, and obelisks tapered with extraordinary control. Not every example is mysterious in the same way, and not every online comparison holds up. But together they create a pattern. Ancient Egyptian stonecraft was not crude. It was systematic, disciplined, and technically ambitious on a level the average popular explanation often fails to convey. Aswan is therefore not just a local curiosity. It is a window into a civilizational capability. And that is why computational analysis, even when preliminary, matters. AI can compare thousands of marks faster than a human observer can. It can quantify curvature, cluster textures, detect recurring geometry, and test whether visible regularity is anecdotal or statistically meaningful. That does not replace archaeology. It strengthens one part of it. It turns impressions into measurements that others can challenge, replicate, refine, or reject. If future studies confirm that the marks show tight geometric regularity beyond what freehand percussion typically produces, then several serious possibilities deserve investigation. One possibility is hybrid quarrying. Workers used dolerite pounders for roughing and fracture initiation, but then employed abrasive smoothing or constrained cutting for final shaping of extraction surfaces. Another possibility is guided manual technology. Pivots, braces, templates, or jigs produced arcs and repeatable tool paths without requiring modern power. A third possibility is specialized abrasive systems. Hard particles, possibly including corundum or similar materials, used with carriers and lubricants in ways not widely appreciated. A fourth possibility is workflow sophistication rather than a single miraculous tool ***. The precision came from sequence, not device, from planning, marking, repeated passes, and controlled material removal over long durations. These possibilities are less glamorous than hidden lasers or Atlantean machinery. They are also more plausible and, in many ways, more impressive. Because if ancient workers achieved these results through deeply refined low-energy systems, then what we are looking at is not evidence of fantasy technology, but evidence of extraordinary engineering intelligence. And that may be the most important point of all. The old habit was to describe ancient workers as if scale and perseverance alone explain everything. As if they just hit stone long enough and history happened. But real engineering is not brute force alone. It is method, sequencing, material knowledge, error control, constraint management, reducing uncertainty, preserving integrity under stress, anticipating fracture, reading the stone before the stone breaks. Aswan speaks in exactly that language. Even the unfinished obelisk tells a more profound story than many finished monuments. It reveals not only success, but vulnerability. A crack appears. The project stops. That means the workers were pushing stone close to the threshold where ambition meets geological reality. They were not amateurs blundering through mass labor. They were specialists operating at a limit. This is why the most responsible conclusion is also the most exciting one. No, the evidence does not force us to say that ancient Egypt had modern industrial machines. No, AI has not solved the granite mystery. No, every unusual mark at Aswan is not proof of a lost civilization. But yes, the quarry marks raise real technical questions. Yes, some visible features appear more regular than simplistic pounding models would predict. Yes, AI-assisted analysis may help quantify that regularity in ways worth testing seriously. Yes, older scholarship, from Petrie onward, already hinted that Egyptian hardstone work involved more sophistication than textbook summaries usually admit. And yes, the current public explanation is often too comfortable for the complexity of the evidence. The deepest value of the recent AI controversy, then, may not lie in any single sensational claim. It may lie in the fact that it forced more people to look again at Aswan with disciplined attention. Not with reflexive dismissal. Not with wild certainty. But with the willingness to ask better questions. How uniform are the marks, really? Which marks belong to which stage of work? Can weathering be separated from original cutting texture? What can controlled replication experiments reproduce, and what can they not? What combinations of pounding, abrasion, lubrication, and guidance best match the surfaces? Can 3D scans, photogrammetry, microscopy, and comparative tool mark analysis resolve categories of mark formation more rigorously than visual inspection alone? These are not fringe questions. They are exactly the questions a mature archaeology should want to answer. Because civilizations are often underestimated when their tools seem too simple for their results. We project our own assumptions backward. We imagine progress as linear and obvious. We assume that if a people lacked our materials or power sources, they must have lacked our level of operational intelligence. History repeatedly proves otherwise. The builders of ancient Egypt were not primitive people producing miracles by accident. They were organized, observant, technically adaptive craftsmen and engineers working at monumental scale. If our present reconstructions fail to explain every trace they left behind, the right response is not mythology. It is deeper investigation. The quarry at Aswan deserves that investigation. The marks deserve it. The unfinished obelisk deserves it. And perhaps the reason this mystery continues to grip people is that it touches something larger than archaeology. It reminds us that the past is not fully domesticated. We have timelines, typologies, tool categories, and institutional narratives. But every so often, the material record pushes back. A surface does not quite match the story. A mark resists the label attached to it. A trench wall under desert light says, in effect, look again. Aswan says that. It has been saying it for a very long time. The granite there still holds the memory of motion, motion we can see in the form of arcs, scoops, and surfaces, but not yet fully name in terms of exact technique. Whether the answer turns out to be advanced abrasive control, guided manual systems, multi-stage quarrying, or some combination we have not yet experimentally reconstructed, the lesson is already clear. The old simplified story is probably not enough. And that is not a failure of archaeology. That is archaeology doing what it should do when confronted by stubborn evidence. Revising, refining, testing again. Artificial intelligence may help accelerate that process, but it cannot replace careful scholarship. It can identify patterns. It can compare geometries. It can highlight anomalies. What it cannot do by itself is decide history. That still requires excavation, publication, replication, and disciplined argument. The danger is treating AI as an oracle. The opportunity is using it as an instrument. If used that way, then the recent attention around Aswan may prove genuinely valuable. Because the mystery has now been reframed in measurable terms. Instead of vaguely saying that the marks look too perfect, researchers can ask how much variation they show, whether their curvature clusters statistically, how their textures compare to experimental percussion, and whether accessibility constraints correlate with irregularity or do not. Those are the kinds of questions that can move a debate forward. And perhaps that is the real threshold we are standing on now. For generations, the Aswan quarry marks lived in the space between wonder and dismissal. People noticed them, commented on them, and moved on. But we may be entering a phase in which the marks themselves become data-rich enough to force a better answer. High-resolution scanning, microscopy, AI-assisted pattern classification, experimental archaeology, and geology together may eventually reconstruct a much more accurate picture of Egyptian quarrying than any single method could provide alone. When that happens, the answer may be less sensational than the loudest headlines promise. It may also be more astonishing. Because the truest surprise in ancient history is often not that people possessed impossible things. It is that they achieved extraordinary results through forms of intelligence we have not bothered to understand deeply enough.